we were discussing about the multiple layer multi-layer neural network design, and we have seen uh, one specific type of learning rule. Uh, it is called as back propagation, right? And in back propagation, we have seen how the delta value that is calculated in the final layer or the output layer can be used, right, to calculate the errors in the hidden layers output, and respective errors of those hidden layers can be calculated first, and they can be used to represent the delta values of each of the what you call hidden layers, right? So after that, then we actually represented in general. The forward calculation gives you the output value in case of multi-layer neural networks using the back propagation technique, whereas when you move from right to left, you will be able to calculate the delta values corresponding to each of the layers output corresponding to an error. Right. Then also we have studied the mathematical representation. Right. After we consider the mathematical representation, we looked at the weight update. Once the weights get updated, then we wrote the general equations, general steps required to implement the back propagation algorithm for any network. So this is what we had seen in the theory part in the previous session. Also, in case of the practical session on MATLAB, right, we wrote a code, and the code is basically corresponding to the function that is back propagation, and we consider the XOR problem, which was not solved by the single layered neural network by applying the delta learning, right? So we consider the same problem. We try to resolve that, right, by applying the back propagation, and then we wrote another code to test this algorithm, right? So wherein we gave several inputs, the same inputs corresponding to the XOR problem, and later on we saw that whenever we run this code, right, it's generating the outputs, right, that are pretty much close to what is expected. All right, so this is our concept that we where we applied the back propagation. Okay, next concept, we want to go ahead and we want to test varieties of right, the modifications that we can do over here, so that we can try to improve the performance, right? So keeping that in mind, now we'll define a new term, and that term is called as the momentum, right, in case of the machine learning deep learning algorithms. So let's move further. So this is called as the it's the momentum. Okay, so this is a concept that is used in the weight updation technique, right? So we are trying to make some changes in the weight updation technique, so that we can try to improve its performance, basically. Okay, so far what we have discussed is that the weight adjustment has relied upon the simplest forms of equations, right? So delta ij has to be calculated. That is a specific layer's weight change that was dependent on the delta value, which was actually dependent on the error value. Okay, and later on we use that delta wij to update the weight, adjust the weight, right? So wij is equal to wij old value plus this delta, right? So these were the equations, right? But actually, there are many other types of weight adjustments possible, right? So normally, if you try to use any other technique or any other advanced weight adjustment formula, we want to gain the speed, right? So first objective is, can you improvise in terms of the speed of calculation? Every input gets a delta wij so that you can update the weight. Can you improve on this in terms of the weight, and can you make it more stable, right? So these are the two objectives now with us, uh, to explore the other options available to perform the weight adjustments. All right, so let us look at that. So whenever the deep learning concepts come into picture, you see we have a huge amount of data coming in, right? That's the first objective, so that the weight update happens several times, not 1, 200 or 10,000. It's much more than that. You might have seen in the previous examples where we try to iterate that with the right, so many iterations. Iterations itself was 1 crore, right? In one of the example we checked that. So in addition to that, the other option is uh, you set the number of hidden layers and the neurons or the nodes inside that hidden layers also you try to increase, right? It's not just 5, 10 or something. Maybe you'll go with the maybe 1000. Let's assume the non-linearity in the classification requirement is too much, means you have to increase the number of neurons and the number of hidden layers. So you see there are, say, crores of iterations that happen, first point, and in each iteration you have, right, thousands or lakhs of neurons weights getting updated, right? So this is actually a huge computation, right? So if you try to improve the performance in terms of speed, you have to find out a way which is quickest in terms of increasing the weight learning rate, weight updation rate. So that's what is important. So we try to cover something which actually deals with the speed of learning, which is called as the momentum. All right. So let's try to define the term momentum over here. Okay. So okay, let me define the term momentum. So momentum can be defined in the following way. So the momentum has a short form that is denoted by small letter m, right? So the momentum is a term that basically gets added to the very fundamental rule which we had considered so far is nothing but the delta rule. So let's try to apply that the concept of momentum to delta rule, and we'll check what's going to happen. So once you are able to apply that to a basic rule, definitely this can be applied to any other, right, advanced rules as well. So let's try to apply the delta rule to the momentum to the delta rule first. All right, so gets added to the delta rule. This is used for, let's say, the adjustment, the weight. Okay, now we have to justify what is the use. Why do you want to add? First question. And once it's added, what is the advantage? Right. So the use of this momentum term, right, is that it drives the weight adjustment to a certain direction to some extent rather than producing a immediate change. So you, right, it will not produce a very immediate change, right? It's going to drive the weight update in certain direction, maybe towards positive direction, negative direction, and so on, right? So okay, the momentum, this particular term drives the weight adjustment to a certain direction. All right. So this will do that rather than if you don't use, this is what is going to happen. So rather than producing an immediate change. So let's try to understand what exactly is going to happen. So normally, if you consider the physical term momentum, that actually comes from physics, right? It is actually going to, what it's going to do, it impedes the reaction of the body to the external force, right? So the same thing is going to be applied here. You see, the concept can be taken from anywhere, right? And you can apply it to any field. That's an example over here, right? So I'm taking the concepts of momentum from physics and I'm trying to apply it to the deep learning or machine learning ANN concepts, right? So let's try to define that. So let me write that point as well, because this is helpful to understand the concept of momentum, why the momentum is required. All right. It is similar to the concept of what is called as the momentum in physics, right? Come on, I can write that momentum which impedes the reaction of the body to the external, say, forces. Same concept, okay? Now let me try to write a mathematical equation, right, for all those concepts which we have applied here. Okay, so let us say we so far we use the change in the weight, that is delta W is equal to, you see, there is a learning rate alpha, then it actually depends on the delta value which is calculated from the error of that particular stage or that particular layer and the input to that layer. Correct? We know this. Now let us try to define what is called as a momentum M. This momentum M can be defined as the delta W that you calculate plus a constant beta into M, say I'll write M bar. Now let me explain this, right? And so the instead of using the delta W to update the weight directly, right? I define the concept of M, right? Which is the change in the weight you had calculated plus a constant times the past value of M. M bar is the past momentum. Okay, so let's see this in detail. So I use M now. So now onwards, the weight can be calculated as the past value of weight. So I'll write old plus M. So you don't use delta W for immediate effect. You calculate a direction from that, that is the momentum. Use the momentum to calculate your updated weight. All right, once this is done, right? Once this is done, then you update the M bar is equal to M, right? This M comes here and gets updated to the M bar. So that when you execute this particular function once again from the beginning, you see that the M bar holds the past value of the momentum of the previous iteration, basically. All right. Okay, so now let me write here. So here, where the M bar, right, is nothing but it is the previous momentum. Is the previous momentum. And let's define a constant called beta. right? It's actually a positive constant. Normally this is less than 1. Okay, now let us try to understand, right? What happened when what is the change that's going to happen when I bring this momentum into picture? Okay, what happens? Let's see. Okay, how the momentum is going to change, because we define that momentum is going to give you a specific direction for the weight update, right? I just have to justify that now. For that reason, let's try to consider some of the initial steps, right, with respect to this momentum, right? So how the momentum changes with the time, let us try to understand. All right, so initially, let me say this is momentum at 0th instant. I'm calling it as m of 0, right? Initial value of m, let me say it is 0. There is no term, let's assume. Okay, once this is updated, right, the m of 1 can be, right, the next iteration, m of 1 will be, see, I'm going just simply going to use the above said equations, right? I have to, m is equal to delta w plus beta times past value, correct? So what is m? That is delta w of the first instant, that is that particular iteration, plus there is a beta into the past value, right? So past value is nothing but, actually it is 0, but let me write it there. So this is m of 0. So this is nothing but, since m of 0 is 0, this is simply delta w of the first. So whatever was the past weight update, weight change you had, that change becomes your momentum in the next case. Okay, let me update. So I'm going to calculate the m in the next interval, m of 2. So m of 2 has to be, you see, this is as per the direct equation, this is the delta w of that instant plus the beta value into the m of 1, right? So you can substitute that now. So this is to be delta w2 plus a beta comes into picture into what is m of 1? M of 1 is delta w1. All right, let's try to write another one or two more values so that we can trace out what exactly is going to happen over here. Okay, so let me write next one, that is m of 3. Let us see. So according to the equation, this has to be delta w of 3 plus a beta value multiplied by the m of the past value, that is 2. So let me substitute, right? So that is delta w3 plus a beta value. Now substitute for m of 2 from the previous equation, that is delta w2 plus a beta into delta w1. All right, so that means m of 3 is equal to delta w3 plus beta times delta w2 plus beta square times delta w1. So this is m of 3. So you can see that the weight update depends upon the past values of weight and the beta value, right? So it is noticeable that these steps that remember the previous weight update as well, right? So M of 3 will contain the effect of the current weight update, previous weight update, the weight update before that, and so on. If you are going for M of 4, 5, 6, 7, you will see that all the weight updates previous to that will be considered in this particular M. Okay. Normally you see that the beta value is less than 1. So older weight update exerts a lesser influence on this particular term, which is the momentum, right? Because the beta is less, so beta square will be much less, beta cube is much lesser. As your weight update gets delayed, so becomes older and older, the effect of that weight update on the current weight update becomes lesser and lesser. That's the another feature of this term momentum. Okay, so whatever we noticed, let's write now. So this can get extended in the same fashion. Okay, you are going to have the similar terms. throughout. You can go to any level of m, right? M of 100, m of 200, fine. Okay, so all right, so we can understand one thing here, right? The previous weight update. The previous weight update. So example, delta W1, delta W2, delta W3, dot, 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 etc. Right? Uh, that those terms gets added. So is added to each of the momentum, right, over the process. This is the first feature that we see. And again, since the value of beta is less than 1, so 0 less than beta less than 1 implies, so I'm multiplying by the beta to every term. So older weight update exerts a very less, and write lesser, influence or the effect on the momentum. Right. Although the influence is going to diminish over the time, very old weight updates remain in the uh, so as the weight update gets older and older, right, those effect of those what you call weight update on the momentum is very less, right? Though the weight update term will be there in the equation, but their effect is going to be very less. That's what is obvious. Okay, so what is our conclusion? Therefore, we can say that the weight is not solely affected by the particular weight updated value. So you can see that there is a stability coming into picture. Why it is stable, right? It is stable in some, the word stable here means immediately you don't take a decision. You see, right, what is the weight change that actually occurred, present, previous, before that, etc. Right? Many terms you consider, right? When you do that, there is what is called as, it's not going in a, right, in random directions always. Like for the current weight update, it is positive weight increase. Next term may decrease the weight change, delta W may be negative, so that next time you reduce, so the effect of the previous training is null because you increase in the previous one, but now I reduce it, means you see the effect of my previous training has been cancelled by the present training. If at all your current data set itself is wrong, so this training actually, right, is made your training, whatever that training took place, right, you can call it as it made it unstable. So we don't want to do that. We want to bring it in a certain direction by looking at all the past uh, weight updates. Okay, so that's what is the basic idea here. So let's write one point just to talk about this, how this brings stability in place, right? So I can write, therefore the weight is not just updated by a particular weight update. So this implies, we can say that the learning stability increases. So ultimately, we can say that the learning stability is going to increase because of this. Right. So what happens as a result? The momentum grows more and more with the weight update. So you see, you are going to get a particular direction as you train with more and more number of training data. So this is going to introduce a direction. That's what is the concept of direction we told earlier, right? So as you increase the weight update, right, the number of weight updates by giving more and more data, you will see that the momentum grows more and more, right? So weight update becomes greater and greater. So learning rate is going to increase as a overall effect of this kind of momentum, and yeah, the trainings using the momentum. So let's add that point as well over here. So the momentum grows more and more with the weight updates. Okay, as you increase, right, as you increase the weight updates, the number of weights that going to update, momentum is also going to grow, right? So this results in, right, as the momentum is going to take a particular direction, weight update is going to be greater and greater. This implies the weight update becomes greater and greater. So overall, I can come to a conclusion that this implies the learning rate ultimately increases. All right. So now our idea is that we want to bring this concept into our code. All right. We'll bring the concept of momentum into the code. So let's directly jump into the MATLAB screen and let's try to implement this over there. Okay. So first of all, what we want to do here is let's try to first let's write a function for this. Right. So let me write a function. I'm going to call it as, okay, edit. Okay, I want to bring the momentum into picture. So back prop, and I'll write an MMT maybe for momentum. Okay, so that's how it becomes easier for us to trace what function is. Okay, so it's a function. So I have to write the, say it's a function. So I have to follow the standard architecture of the procedure. So it's a function. I'm going to return two values of weights W1 and W2 is equal to, so write the name of the same function which you have given for the file. So this is back MMT, and let us try to update this function with the what we are passing, right? So what you're passing first, you have to pass the weights. So W1 will be passed to this, W2 will be passed to this. Then we have the input vector, that is X, and the desired or the targets. Okay, this is what we are passing, right? Now you see, previously we used to define one value called learning rate, right? What is the learning rate? That is alpha. Okay, alpha is equal to say 0.85, 0.8, 0.9 will work fine. Okay, you can make any value over this, any range. This, and let's see now, you see that the equation of momentum defined another term, that is beta. right? So let's define that beta. Right? So beta is equal to, I'll make it 0.9. Maybe you can, when you run the code, right, you just make sure that you put different values of alpha and beta and look at the effect, right? Make a note of effect. What happens to the learning when the alpha is say 0.5, right? What happens when this is very close to 1, like 0.99? You can make a table of this results, so that, right, you can understand the effects of these coefficients of the constants. Okay, same thing you can do with the beta. We can make beta is 0.85, 0.8, 0.5, 0.2, and right, look at the effect, right? So like that you can make a table and just make it, okay, it took long time, so if the result is not accurate, like that you can make a comment over there. That's going to help you a lot. All right, okay, then let me define the momentum terms, right? I'll define MMT. Say first one, that's I'm going to define this is equal to, so how many momentums you need, equal to the number of weights, right? So this is, I'll define it as zeros initially. It's a zeros of, so the size of the W1. Similarly, define momentum 2. Okay, this is equal to, again, zeros of size. What is the size? This should be that of the size should be, its size should be that of the size of W2 itself. Okay. Now that defines the momentum terms. We initialized with zeros. Okay, that's fine. Let's move ahead. Let's go to the number of training data, that is equal to 4. Once again, we are implementing the XOR itself. Okay, right. Then say for the I is equal to, this is 1, 2, n. Okay, actually 4, but I can write 1 to n. Okay, for all such values, define the extract one row from your input vector and put it into a smaller vector called x. X is equal to capital X of I means that row, all the rows, but uh, sorry, ith row, but all the columns. Okay, that's it. Make it a column vector, that is x. Then d desired value is equal to capital D of, okay, d is done. Let's go for the v1. How do you calculate a v1? V1 is nothing but, it is a w1 into x. Right? You got a v1, convert this into the y1, right? The output of the first hidden layer, right? What is that? That is my sigmoid of y1. Okay, not y1, my mistake. I think this should be v1, right? Okay, so I get this. Now use this y to calculate the error first, right? So error E should be equal to the desired value D minus the y value. Okay, let me make some changes. Let me make the oh, okay. There is a mistake, right? See, I considered only first layer. This is the first layer, correct? But I need a second layer output as well. Then only I can go for error, right? So sorry, there is a mistake. So actually, first let me write that part first, then I'll come back. Okay, so I use v1 to calculate the y1 using the sigmoid function. Now use this to calculate the partial output of the second layer, that is output layer. So v is nothing but the weight 2, right, getting multiplied with the past output, so that is y1. Okay, now use this v to calculate the final output y. So y should be equal to my sigmoid of say v. Okay, So that actually calculates the output. Now use this output to calculate the error. So E is equal to the final error at the output layer, that is D minus Y. All right, so that is done. Now use this to calculate a delta, right, like earlier. So how do you calculate a delta? Delta is equal to the differentiation of the phi, which is nothing but y into 1 minus y into error. All right, so this is the output. Y should be dot star 1 minus y, again dot star the error E. This gives you the delta value, right? Use this delta value to calculate the error E1, right? Error E1 corresponds to the error of the previous layer, which is a hidden layer, right? So E1 is equal to the weight of that, the second layer, which is W2 transpose, right? Multiply that with the delta value. It's a delta, okay? Use this to calculate the delta 1, right? Corresponding to the hidden layer's delta value. That is equal to, now I just have to use the y value of this layer, which is denoted by y1. Okay, this is y1 dot star 1 minus y1. It's 1 minus 1 dot star. I have to use the error of that layer, so I think we have given a name as E1 to. Okay, right? So we got this. Now whatever code I'm writing now, that is corresponding to the momentum. So just check, right? So we have to calculate a delta W1 first. So denoted that as dW1. What is dW1? By definition, this is nothing but the alpha, right? Multiply this with delta 1, multiply that with the input vector, that is x. We have to take it transpose. Okay, that is nice. Next, I'm defining MMT1. So what is the momentum of this particular layer? It is defined as dW1 plus, if you remember, I have to use a beta and the past value of this, correct? So beta, multiply that with a past value of that is MMT1 itself. Okay, now use this momentum to calculate the weight. So first weight is W1. W1 is equal to past value of W1 plus, right, the MMT1. So simple, just I'm adding 2 lines of code, that's all, to the whole concept. But I have to repeat this as many number of weights I have, right? So I do the same thing. dW2 is equal to a alpha value multiplied by delta value into the input to this layer becomes the y1 dash. Okay, that's the input to this layer. And once I have this value with me, I have to do what is called as the updation of MMT. So MMT2 for this layer has to be dW2 plus the beta value into MMT2, the past value of MMT, right? And update the weight. So W2 is equal to the W2 plus MMT2. All right, so that's the updation. I think we are inside a for loop. I just have to end the for loop now. So this is end of the for loop. Then I'll end the function itself, because function returns W1 and W2, right? So we are able to return that now because the W1 and W2 get updated like this, which we can see over here. Okay, so basically we initialized the W1, W2 as zeros. oh sorry, some randomly we will initialize. MMT1 and MM2 will be initialized as zeros, right? And as you proceed further, this gets a direction, right? As you increase the number of training, this is going to be increasing the uh, particular particular momentum in a direction. Okay, so this is, let's save this. So we'll test this part of the code when we type another code and run that part of the code. Okay, so let me write another code. So I'm going to call that as edit. So I'm going to test this now. So test the, so test back propagation and empty. So we open a new file. All right, now let's try to run this. In order to test this, right, we need to write a code to give the input data first, and then we'll call the function, and the function will then will run this part of the code, and it tests this. All right, so let's uh, do the and CLC. Okay, let's go to the x is equal to, open the bracket. So give the same data 0, 1. This is going to be the class 1. Then I'll give a class 0, 0, 0, 1. Then I'll give another class that is 1, 0, 1. This is also 1. And I'll give the last data which belongs to class 0, 1, 1, 1. All right, so that is x, followed by, let's write the desired, the target values. First one, 0, 1, that is 1. Second one is 0. Third one is 1. Last one is 0. Okay, so this is the desired. Okay, now initialize the weights. So w1, like the previous case, we defined this in a random fashion. All right, so let me write 4.5 into, let me write, I want to create a rand, R-A-N-D, between zeros and ones, but it will be, what is the size? So size of the first layer, if you remember, the size of the first layer depends upon the number of inputs, right, that I try to give, right? There are, right, 4 neurons in the next layer, and there are 3 inputs, right? So the number of inputs will come, right, at a second as a number of columns, and the number of neurons you have in the next layer is in the first step. So I have to write this as 4, right? 4 rows, 3 columns. Okay, minus say 2.5. Okay, so I'll write a W2 now. So if you remember, the output layer has only one neuron. So this has to be say 2.5 times random. See, this is the number of neurons you are connecting is just one after this, right? So, and how many outputs that you're connecting to this neuron? There are 4 outputs because the previous layer has 4 neurons. So this is minus, let me write say 1.25. Okay, so create something at random. Then for, right, let's do the epoch. For epoch is equal to, say, starting from 1 till, let me keep 1000. For 1000 epochs, do the training. How do you train? You call the function which you had written. Okay, so function results in outputs, that is, say, capital W1 and W2 equals to, right, call the function. The function has a name, back prop mmt, and pass the inputs. So inputs are W1, W2, the input, that is x, and the desired value d. So we pass it. So once you pass these values, the function will run and you get the results in W1 and W2, which are the updated values. So finish the loop by an end. Okay. Next, n equals to say 4. Then for j equals to 1 to n, x equals to capital X of the j, comma, all the columns, take a transpose. All right. Then once you give this, I don't need the desired now. It's not a training, right? So no desired is required. Simply pass the input one by one, calculate the V1 is equal to the W1 into input. W1 into X, right? Then we have the Y1 equals to my sigmoid of that value, which is V1. This gives you the output 1. And use this Y1 to calculate a V is equal to the weight W2 into Y1. Okay, then final value Y is equal to my sigmoid of this V. Okay, then and okay, so this actually is the code required to test the function, that is the back propagation, which is implemented using the concept of MMT as well. All right, let's try to run this first. Yeah, it's running, so I can create a Y as this now. So let me write this is Y of J. Let's make this an array, and I don't want to display here. I want to display the value of Y at the end. Okay, so I'll just type Y here so that it gets printed. So you can see it's 0.9.02. These are closer, but there is ambiguity over here. Whether it is 1 or 0, we cannot make a conclusion. This is obvious because only 1000 iterations have been done, right? Let's increase. So let's increase and see the effect, right? You can see this is when it is 10,000, 0.9, 0.03003, close to 0, 0.99, 5.0. So this result was in all the previous cases, if you compare, right, this result was coming after a huge number of iteration, like 10 lakhs or something. When you did that, then we used to, right, get this kind of results, right? Closer result was coming after 1 lakh or something. Now you see it is coming within 10,000, right? See, the number of training is the epochs have been reduced, indicating that your learning is faster. So this is what we discussed. We wanted basically to increase the performance of the back propagation algorithm, right, by using some technique, right? So that technique should be increasing the speed first, and the learning should be appropriate in terms of the stability. It should be giving you a proper direction in which the weight gets updated, right? Both the things are happening here. You can see that the weight is updated quickly within 10,000 iterations, and this result is good, right? So definitely, if you do another iteration of the next by adding a 0 to this, definitely this is going to be much closer. You see, it's more and more appropriate. We were expecting 1010, so it's coming like 0.99, 0.00, 0.99, 0.00, which is like, right? Yes, it which indicates that yes, whatever you are, whatever you have implemented, the whole concept of momentum, basically it increased, right, our what you call as learning rate, as well as the stability of our the coding, the concept of back propagation algorithm, its stability is also increased, right? So overall, we can conclude